Okay, so a few videos ago, we differentiated the function y equals x squared by working through this limit you see here. Okay, the idea was to grab 2 points on the curve, to calculate the gradient between them, the straight line gradient, which is what this huge fraction does, and then take the limit of this gradient as the distance between the 2 points approaches 0. Now, since then, we've taken a detour into the world of limits to make all that work a little bit more precise. But along the way, we found out that limits don't always exist. And the consequence of this is that not all functions can be differentiated. A lot of functions simply don't have a sensible gradient function that works for every value of x you can feed it. And back in the previous video, I made vague allusions to the fact that a curve has to be sufficiently smooth for our work to make sense, and in this video we'll be aiming to make that a little bit more precise, mostly by showing you how it breaks and what it looks like when you can't differentiate a function. The good news is we've done all the hard work we need to almost immediately state what it means for a function to be differentiable, which just means it's possible to differentiate, right? To be differentiable means there should exist a sensible gradient function that works for every value of x you can give it. And the condition is simply that this limit must exist for all values of x in the domain of f. Now, there's a really important relationship between this idea and continuity, which is that we need continuity for this to have any hope of working. Okay, you can probably imagine that asking for a gradient is all kinds of nonsense if your graph is jumping around, not continuously. Okay, and the language we often use is that continuity is a necessary condition. So a function must be continuous to have any hope of being differentiable. But be careful. Just because a function is continuous does not guarantee that it is automatically differentiable, and we'll be seeing a couple of examples of this in a moment. The language we use is that while continuity is a necessary condition to be differentiable, it is not sufficient. So there is no guarantee that just because you're continuous, you're also differentiable. And so to picture what we mean by this, suppose we have a bubble containing all possible continuous functions. Then the bubble containing all possible differentiable functions would fit inside this big red bubble, meaning all differentiable functions must also be inside the space of continuous functions. Okay, but there are some continuous functions that fail to be differentiable. So let's take a closer look at these functions now, and we'll start with y equaling the absolute value of x. We'll draw this, and so we'll take our usual y equals x graph. We grab the part below the y-axis, the bit where the y value would be negative, and then we flip him up to be positive. Then let's say we try to draw the gradient function, so a function tracking the gradient of this guy at every value of x. We'll start up the top left corner here, and this is where we're on a diagonal line going downhill. So the gradient must be -1 down here. And the line is straight, so it stays at -1 all the way across to here. And now at this point, once we move any further to the right, we'll be on an uphill diagonal line, so the gradient switches to being +1. And it stays that way forever. Okay, so clearly the point of concern will be what on earth is going on at x equals 0 here. Okay, now just a disclaimer, derivatives, so gradient functions, actually do not need to be continuous. But this case right here is still super fishy. Okay, so we'll take a closer look at what's going on at this point. Okay, so remember the whole idea behind a derivative was to get real close to the point, to push it the tiniest bit across on the graph, to calculate the gradient between these 2 points, and then to take the limit of this gradient as the distance between the 2 points goes all the way to 0, or approaches 0. Okay? And this last thing I said is where everything stuffs up. Because if you remember what we said about limits previously, for the limit to exist and make sense, we need it to be approaching the same value from all directions. But the moment we take any step to the left, no matter how close, the gradient we get is going to be -1. And so if we're trying to get the limit of the gradient as the distance between the points goes to 0, well, it doesn't matter how close you push those points together, the gradient to the right is stuck at 1, and the gradient to the left is stuck at -1. So you're going to have these two conflicting values. The limit can't decide between positive and -1, and so the limit does not exist. There's no sensible gradient to assign to this point where x equals 0. And so because the limit of the gradient does not exist at that point, we say that this function is not differentiable at x equals 0. Now, this is just an illustration of a more general case where functions actually cannot be differentiable at any kind of sharp corner. Okay, try and draw a few pictures and play around with this idea yourself, but the key point is that whenever you have a sharp corner, the gradient to the right and the gradient to the left will always be conflicting, and it will break the limit in the exact same way as we've just seen. Okay, so moving on to our next example then, we're going to take y equals the cube root of x. You may not have seen a graph of this, but because a cube root is the opposite of cubing, you can actually just graph y equals x cubed, which I'm sure you have seen before. And then we're just going to switch the x and y axes around. Okay, that will just reverse the function, giving us the graph we want. Okay, so let's do the same thing and draw a gradient function starting from the left. We have a rather shallow slope here, but it is still going uphill, leading to a small positive gradient. And as we travel towards x equals 0, we notice it quite quickly starts becoming super steep. And actually, the same thing will happen on the right-hand side. It is symmetric after all. So if you go really far to the right, it's super shallow, but as you come back towards x equals 0, it goes mad steep again. And so again, we find something weird is going on at x equals 0. In fact, the whole problem here comes from the fact that the tangent at this point, this arrow I've drawn here in red, is completely vertical. And in that case, where the tangent is completely vertical, the gradient as you approach this point is, as you can see from the graph, actually shooting off towards infinity. And the consequence of this is that we cannot possibly assign any number to the limit of this gradient as we approach 0. It just keeps on increasing. It goes almost infinite, we would say. So the limit doesn't exist. And so this function is also not differentiable at x equals 0. And we can generalize this as well. This time the culprit isn't a sharp corner. It's actually a point where the graph just goes vertical. And so when you have a vertical sort of point there, this isn't technical by the way, I'm just saying this, I'm sure you know what I mean. When the graph goes vertical, the gradient is shooting off to infinity there, and so that breaks our limit definition. Okay, and so those are two examples, two simple cases of how functions can fail to be differentiable. Okay, now while the function we would say is not differentiable, we can actually still calculate a derivative and a gradient almost everywhere. So the left case, you can see it's -1 on the left, it's 1 on the right. There's just one point that breaks that. Now 1 point is enough to break the whole function, but the truth is, and the reality is, practically, you can still calculate the gradient of these at all the other points that are not problematic, so anywhere where x is not 0, but that will be for another time. Okay, so thanks for watching this one, we'll see you next time.